Hi guys, Harry here. Welcome to Scrap Science. The first thing you'll probably notice is that I'm at a different desk than I'm normally at. I just put this one together just then for this video because the desk that I normally use is all the space is taken up by this distillation that I've got going for the heavy water. The next heavy water video I thought it was going to come out pretty soon, but we've had a couple of setbacks in the process, so it might be a while before you see any of that. Anyway, so last video we made some ammonia, and I said at the start of that video that we were going to use the ammonia to isolate nitrogen gas. And to generate that nitrogen gas, what we're going to do is electrolyze our solution of ammonia. It's going to be very similar to the standard electrolysis of water, which generates very pure hydrogen and oxygen gas. But in this case, of course, we're going to be generating very pure hydrogen and nitrogen gas. So what I've just set up here is a beaker with a little bit of our ammonia solution in there, and we've got two graphite electrodes sticking in ready for the electrolysis. And so if we just connect up this to our power supply, I've got it connected to 5 volts, and if we turn that on, what we should start to see is hydrogen gas being generated. Actually, this would be the cathode, and nitrogen gas should be generated over at the anode over here. Now obviously we can't really do much with this kind of setup. We can't really get the nitrogen gas off of that electrode, and so what I've put together over here is this little piece of PVC pipe with 3 carbon electrodes within it that should be able to capture all the nitrogen gas, and I've got this tube coming off it so that we should be able to feed it into whatever we want. And so what I've just set up now is we've got our PVC pipe ready to collect the nitrogen gas that comes off the anode, and we've got just another graphite cathode there generating the hydrogen. That's the stuff we don't want, so we're not collecting any of that. And we've got the tube that'll carry the nitrogen gas going into some water, so we should be able to see it bubble out. And what I'll do now is fill this up with some ammonia solution, and we'll turn the power supply on, and we'll see if we can get any nitrogen gas to flow through the tube. Alright, so I have poured some ammonia in there. We've got all the electrodes set up, power supply's all set up. I've got a multimeter in series to measure the current, and so if we turn it on, we should see we've got 0.6. It's dropping off. That's because the gas generated on the electrodes blocks some of the current, but we're getting a bit over half an amp, and you can see that we're getting quite a bit of hydrogen gas coming off the cathode, and of course you can't see the nitrogen gas being generated by the anode, but hopefully we should get some nitrogen bubbling through this tube here. So now I've left it going for a minute and I haven't seen any bubbles. If we just move the tube up a little bit in the water, we should see maybe, there we are, a little bit of nitrogen gas come out, but the reaction is so slow at 0.6 amps that we're not generating enough nitrogen gas. Each nitrogen gas molecule requires 6 electrons to pass through, as opposed to hydrogen, which only needs 2 electrons to pass through to make a molecule of hydrogen. So the rate of production of the gas will be 3 times slower than that of hydrogen, and you can see we're not actually generating all that much hydrogen. So what I'm going to do to fix that is I'm just going to connect it up to, if we can focus, there we are. I'm going to connect it up to 12 volts. Hopefully there's not too much current that flows. 2.5 amps, that's a fair bit. Yeah. Anyway, we'll just run it like that for a little bit. We don't want it to heat up too much, and hopefully we should see some gas bubble through this tube. And you can see it's just starting to bubble through now. We should get another bubble in a bit as I say that. There we are, a couple of bubbles. It is pretty slow, but we are generating very pure nitrogen gas. I'm just going to leave this going for a little bit to let all of the air that's in the chamber there kind of purge out, and hopefully then we'll be getting some more pure nitrogen gas, because right now it's mixed with all the air that's in there. Now while that's going, there are a couple of good things about this reaction. According to a paper that I read online, this reaction actually only needs less than 1/10 of a volt to actually run. Of course, we're running it at 12 volts just to get a higher current, but compared to the electrolysis of water, which requires at least 1.23 volts, I think, this reaction requiring less than 1/10 of a volt obviously requires a lot less energy to generate hydrogen gas for any need that you might have for hydrogen gas. I don't know. But of course, you have to make the ammonia from hydrogen gas through the Haber process, so it's not really that useful. Another good thing is that the anode, that's the one generating the nitrogen, in the electrolysis of water, the anode would be generating oxygen gas, and generating oxygen gas kind of destroys the anode a little bit. You can see there it's kind of eroded away a little bit, but because the formation of nitrogen gas requires a lot less energy, I'm thinking that the carbon electrodes should fare a fair bit better. And we can already see that there's no carbon particles in the water just yet, so it's looking good. This is still just bubbling away, I think. There we are, yep. So a little bit longer and then we'll start to collect the nitrogen gas that we've got coming up here, because hopefully all of the air will have been purged out. All right, we're getting over 3 amps now at 12 volts, and that's what, 36 watts flowing through this solution, which I'm not too happy with, because that's probably going to warm up the ammonia quite a bit, and I don't really want 3 amps flowing through these wires for too long. The rate of production isn't all that great, so I'm hoping that when we switch it back to 5 volts, yeah, we got nearly 1 amp, that's alright. We'll just let that go and cope with having a lower gas production rate, because that's a much better current, in my opinion, to be flowing through that. It's like less than 5 watts, so we're good. One thing to note actually is that the current that we've got flowing between the two electrodes is due to the ions that are in solution, and those ions don't actually come from the ammonia itself, because the ammonia solution is just, it's not NH4OH or ammonium hydroxide. When it dissolves in water, it actually just remains as ammonia in a mixture with water, and so the ions that provide that allow for the current to flow are actually from the impurities from when we made the ammonia. There's like sulfates, maybe some hydroxide, acetate in there. So it's all those ions that are actually in the solution that are allowing the current to flow. I'm pretty sure that a pure solution of ammonia wouldn't actually be very conductive at all, similar to how distilled water isn't very conductive. So it's actually been a couple of hours now. You can see it's getting a little bit more murky, so obviously the graphite anode is kind of falling apart a little bit, but that's alright. Hopefully all the air has left the chamber and the tube, and so what I'm going to do is I'm going to invert this graduated cylinder and stick it over there and see if we can collect all of the nitrogen gas that we are generating. So you can see I've got the graduated cylinder inverted over the top of where the gas is being let out of the tube, and we've already got about a bit over 1 milliliter worth of gas, so that's pretty good. I think I'll leave it on 5 volts. We've got a good enough gas production there. So yeah, it's already generated, I don't know, 2 milliliters in a couple of minutes, so that's pretty good. We'll leave that going for a little bit, fill up the graduated cylinder, and then we'll do a couple of gas tests to tell whether it's nitrogen. Actually, I do kind of want to see how well 12 volts will do, so let's do that. Got 2.5 amps flowing. It's bubbling quite furiously with hydrogen, and hopefully we should see some more frequent bubbling through there. Yeah, there we are. Nice. Alright, so I'll wait till that fills up and then we'll take it out. Also, I forgot to mention before, but I'm pretty sure I'm the first person on YouTube to actually try this reaction, because I have had a look and I don't think anyone else has had a go at generating nitrogen by electrolysis. Most people generate nitrogen from, I think it's sodium nitrite and ammonium something. I don't know, I'll put it up on screen. But of course I can't, well, I'm in Australia, I can't really get hold of any sodium nitrite, so I think we'll just stick with this method, even if it's a bit slow. Alright, you can see it's close to filling up the graduated cylinder. Just a few more bubbles and we should be done. And so we've reached the point where the bubbles no longer go into the graduated cylinder, so we're all done. There we are. So first of all, turn the power supply off, disconnect everything. That'll stop the reaction, and we have our maybe 10 to 15 milliliters worth of nitrogen gas. And there we go, our nitrogen gas. We don't have too much, but it is hopefully very pure. I mean, there'll be some ammonia vapor in there, maybe. Anyway, I think the only thing we need to do is check that it's not either hydrogen or oxygen, because those are the two gases that you might expect to be generated by electrolysis. So what we'll do is we'll just light a match, stick it in there, and if it pops, it's hydrogen. If it stays lit, it's oxygen, and if it just goes out, then we know that we have generated pure nitrogen gas. Now, while nitrogen is less dense than air, it is only marginally so. I mean, it makes up 80% of air itself, so it should actually, when I take off the tape, it should actually stay in the graduated cylinder for a fair while before all the air kind of mixes in with it, so we should have time to do match test. Alright, I need both my hands for this, so let's take the tape off, and quick, I can get the match to light. You'll notice that the match just goes straight out. So I'm pretty sure we do have nitrogen gas, and we should have nitrogen gas anyway. That's how the electrolysis should work. So yeah, there you go. We did have nitrogen gas. It's probably all gone now. But using electrolysis of ammonia, you can generate nitrogen gas on the anode for not very much energy at all, really. The reaction is actually pretty easy to explain. You can see I've got a diagram set up here. The only things that we need to worry about in solution are the ammonia and the water. The other ions that actually allow for the electricity to flow, they're just spectators and they don't actually take part in the reaction. So we've got a power supply here. This is our anode and this is our cathode. And so if we say have 3 electrons flow from the negative of the power supply into the cathode, that'll react with 3 water molecules, and what that'll do is produce 3 atoms of hydrogen, and they'll bubble out as hydrogen gas. What will be left over is some hydroxide ions. And now over at the anode, if we do the same thing, if we're taking 3 electrons from the anode side of the reaction, what that's going to do is that's going to take 3 electrons from one of these ammonia molecules and release the nitrogen in it as nitrogen gas, which will come up as bubbles, and then it'll leave behind 3 H plus ions. What will finally happen then is all of the H plus ions will react with the hydroxide ions and just giving us water again. So we're not actually losing water in this reaction. The only thing that's actually being consumed is ammonia. And so the overall reaction of this setup is ammonia, if we have 2 of those, will be producing nitrogen gas and 3 times the volume of nitrogen gas as hydrogen gas over on the cathode. Like I said before, this reaction doesn't actually require very much energy at all. That's due to the electrode potentials at each electrode to produce hydrogen gas from a basic solution that requires negative 0.82 volts. And then over here generating nitrogen gas from ammonia at the anode takes negative 0.77 volts. And so the difference between those two voltages gives us our total required voltage between the two electrodes as 0.059 volts. It doesn't quite add up, but that's because these decimal places don't go to 3 decimal places. And you'll notice that 0.059 volts to generate hydrogen gas is a lot better than the 1.23 volts required for splitting hydrogen from just regular water in a basic solution. Something that I actually believe is being researched currently is the use of ammonia for hydrogen storage, seeing as it's really easy to generate hydrogen from the ammonia. Just like this, you can use it as a way of storing hydrogen gas. Anyway, despite all that not being a very viable way of generating any kind of large quantities of nitrogen gas, I hope you found that interesting. See you later.